Welcome to our session number 30. In today's section, we're going to be continuing on the metal oxide semiconductor structure. We'll have a bit of a review of the structure of the topics we talked about during our last session, and then we'll go on to band bending in something called the NMOS, and we'll define what NMOS is. It was one of the terms that we talked about last time. We didn't define it. And then we'll talk about, we'll go into some examples, a little bit of mathematics here, hopefully not too challenging, and then we'll talk at least qualitatively about the really important topic of threshold. And if we have time, we'll at least start a discussion, I hope, in capacitors in series. And the reason that we want to talk about capacitors in series is because the metal oxide semiconductor structure, the NMOS structure, has two capacitors in series. They are the oxide capacitance and the depletion capacitance in the silicon. But first, let's listen to a wonderful opera, an aria from the wonderful opera The Barber of Seville by Rossini. We're going to be listening to the Largo al Factotum. Factotum, I guess in English, you would call the jack of all trades, and that is Figaro. He is indeed the jack of all trades. Among his many qualifications, he is a barber, he is a physician, and he's even a matchmaker. My favorite line in the aria is "Una alla volta, per carità," one at a time, for goodness sakes. And I had that as a sign on my office door because things get hectic. And let's listen to Largo al Factotum, and we'll see you in about 4 minutes.
La 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 la, la 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 la, la 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 la. Larga fatotum della città, largo. La 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 la. Resta bottega che l'albeggia, resto. La 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 la. Ah, che bel vivere, che bel piacere, che bel piacere per un barbiere di qualità, di qualità. Ah, bravo Figaro, bravo, bravissimo, bravo. La 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 la. Fortunatissimo per verità, bravo. La 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 la. Fortunatissimo per verità, fortunatissimo per verità. La 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 la. Pronto a far tutto la notte e il giorno, sempre d'intorno in giro sta, miglior cuccagna per un barbiere, vita più nobile non si dà. La 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 la. Raso e pettini, lancete forbici al mio comando, tutto qui sta. Lancete forbici, raso e pettini al mio comando, tutto qui sta. Vera risorsa, poi del mestiere, con la donnetta, col cavaliere, con la donnetta, la 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 lera, col cavaliere, la 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 la, la la. Ah, che bel vivere, che bel piacere, che bel piacere per un barbiere di qualità, di qualità. Tutti mi chiedono, tutti mi vogliono, donne e ragazzi, vecchie fanciulle, alla parrucca, presso la barba, con la sanguigna, presso il biglietto, tutti mi chiedono, tutti mi vogliono, tutti mi chiedono, tutti mi vogliono, con la parrucca, presso la barba, presso il biglietto, ehi, Figaro, ahimè, che furia, ahimè, che folla, uno alla volta, per carità, uno alla volta, per carità. Figaro, son qua, ehi, Figaro, son qua, Figaro là, Figaro qua, Figaro là, Figaro su, Figaro giù, Figaro su, Figaro giù. Molto pochissimo so come il fulmine con il factotum della città, della città, della città, della città, della città. Ah, bravo Figaro, bravo, bravissimo, ah, bravo Figaro, bravo, bravissimo, a te fortuna, non mancherà. A te fortuna, non mancherà. Sono il factotum della città, sono il factotum della città, della città.
Okay, so this is a outline of some of the topics we'll be covering in today's session. As we said, we're going to start with a review. We're going to look at part of this wide range of different structures that we can have in the metal oxide semiconductor capacitor, also known as MOSFET. And specifically, we're going to start with depletion, and we're going to see how we can go from depletion into flat band and into accumulation by applying a negative bias. And we'll see what that's all about. Then we're going to look at the entire structure in pictures. So this is very qualitative. And then we're going to go back and go from accumulation to depletion, and we're going to keep going the other direction. Here we go from depletion to accumulation. Here we're going to start from accumulation, go to depletion, keep going to weak inversion, and then to strong inversion. Then we're going to look a little bit on the quantitative side, band bending in NMOS. We'll have to define what NMOS is. And then finally, we'll look at some examples and special cases. And if we have time, we'll start on threshold and adding capacitors in series, and finally we'll end with a short video clip. Okay, so let's get started. This is a structure that has no applied bias. The only thing we've done is we have connected the silicon to the metal through the backside. There's a wire that goes around here, so we have a connection between the silicon and the metal. We've allowed the Fermi levels to equilibrate, and it works out because of the difference in the work functions that there is a depletion region with W, and because this is P silicon, I probably should have made this a little bit larger, then we have negative fixed ions in the depletion region. We have positive surface charge at the metal oxide junction, and therefore we have a internal electric field which goes from left to right in the positive direction. Now, we apply a negative bias. What does that mean? We make this part here, the surface, more negative than it was. So we apply a negative bias here, which means there's a positive bias. This is external, E external, and therefore we oppose the internal. Opposing the internal, we know, is a forward bias. So if it's a forward bias, the band bending decreases, and that's exactly what we're showing here. The band bending, excuse me, the band bending here is greater with no applied bias. With a forward applied bias, the band bending becomes less, and eventually we go to flat band, and the flat band is no band bending at all. The bands are flat, and at flat band there is no charge. Here there's just a little bit of negative charge and just a little bit of positive charge in the depletion region. The W has shrunk very dramatically, and if we keep applying a negative bias, we get to a situation where we get to flat band, and flat band is equal in magnitude. We're not worried about the sign right now. Flat band is equal in magnitude to the difference in the work functions phi sub m minus phi sub s. Okay, so let's assume we've hit flat band, bands are negative, and we keep going. So we keep going with a more negative voltage than flat band. Flat band here, it's going to work out for most cases, flat band for a p-type silicon is on the order of a volt. So we're going to see that would be obviously minus 1 volt in order to flatten the bands. So therefore we're going to say that the flat band voltage, the external voltage that we need to apply on the gate to completely unbend the bands, will be minus 1 volt. And we say also, if we have the same structure, we're not going to do that, but if we had the same structure for N silicon, same idea, the same conditions, we would have a flat band voltage of about plus 1 volt. Okay, so now what we're going to do is apply a voltage, an external voltage, which is more negative than minus 1 volt, say minus 1.5 volts or minus 2 volts. In that case, these bands are going to bend up a little bit. We're going to make the surface here of the junction between the metal and the oxide even more negative, and then we're going to make the surface here at the oxide P silicon junction, we're going to make more positive. Well, that's pretty easy to do because we've got lots of holes here. So therefore, we're going to have just a simple capacitor. There is no depletion capacitance at all. Here there's a fairly nice depletion capacitance due to the band bending. So this region here would be our depletion capacitor. So we really have two capacitors here. We have the oxide capacitance, and we have the depletion capacitance. Also notice that the band bending in the oxide is in the same general direction as the band bending in the silicon. But if we have accumulation, we have just a little bit of band, a really tiny bit of band bending up rather than down, and we have a negative bias here, and or I say negative charge here, and positive charge at this point. And since it's simply just a capacitor, we can write the capacitance relationship. The charge is equal to the capacitance multiplied by the applied voltage, and the applied voltage in this case is just the VG more than the flat band. In fact, it's more negative. We're going to do some examples to see how this works in just a little bit. And of course, the oxide is just the oxide, I should say the capacitance is just the oxide capacitance, and the accumulation charge we call VACC, V accumulation. So that's pretty much it for the review from depletion to flat band to accumulation. And now we're going the other direction. So if we move the external bias back to flat band, which is to say we make it more positive than it was minus, in accumulation it's about minus 1.5 volts or so. So we go back to flat band, and then we continue. So we continue to make the external bias, the external voltage, more and more positive. So we're in now big depletion, or depletion big time. Now the voltage drop across the silicon also increases because the band bending increases. And the voltage drop across the oxide increases. They both increase, but now we have two increases and two capacitors. And of course, just like in the accumulation mode, there is charge on the metal oxide interface. That's right here. And there is charge in the depletion region here. But of course now the charge is positive at this interface, and it is negative in the depletion region, which grows, and the band bending gets pretty severe, or gets bigger anyway. Okay, now let's see what we do. Okay, and if we increase this positive voltage even further, I say positive voltage, I mean V sub G, make it more positive, we can make a situation in which the surface right here goes to be negative electrons. And let's see what that is. And that's a really big deal. And that's depicted in this diagram, figure 17.9. The voltage, external voltage VG, is so large that the intrinsic level crosses the Fermi level in the silicon. And at this point right here, because the Fermi level is now above intrinsic, this surface layer right here becomes not only negative fixed ions, it becomes electrons. So now we have inverted the substrate, P in the bulk and N at the surface. And this is summarized in the table here, table 17.1. This is the one we're going to be using for P-silicon. In accumulation, the bands bend up. The band bending is very shallow, and we neglect it. Flat banding, there's no band bending. Flat band, there's no band bending. In depletion, the bands bend down, and all this as we're making the gate voltage more and more positive. Inversion, and we're not going to say what kind of inversion right now, because there's two flavors. In inversion, the bands bend down sufficiently to cause electrons to accumulate. Perhaps I shouldn't use the word accumulate, because this is not the accumulation mode. To gather at the interface. So in inversion, this surface, the junction between the oxide and the silicon, inverts from P to N, and that is what we refer to as NMOS. NMOS. And that's why we call this structure an NMOS structure. And in the N-type silicon, everything is completely reversed. Wherever you see up, there is down. Wherever you see up here, wherever you see up here, there is down here, and it's the same deal. And if we make the external bias so negative that the bands bend up sufficiently to invert the N silicon, we get PMOS, because N converts into P at the surface. Okay, so we can look at that pictorially, and this is rather crude, and it's completely qualitative, but just to give us a sort of strengthen our familiarity with all this, again is for P silicon. In accumulation, we have generally an external negative bias at the metal oxide interface and positive charge in the silicon, and we just basically have a simple parallel plate capacitor. In depletion, we put a more positive bias in the metal, external, and we have positive charge at the metal oxide interface and negative charge, fixed ions. Negative charge consists of fixed ions in the P silicon. And then in inversion, we have not only negative fixed ions in the P silicon, we have a surface charge, an inversion layer at the surface, and this is going to characterize the field effect transistor. It is this layer which will cause a channel for conduction between two electrodes. I'm going to stick an electrode down here, and I'm going to stick an electrode up here, and we can use this channel to conduct electricity, and we can control that conductivity. We can make a resistor or transistor by controlling the channel conductivity. And this paragraph basically summarizes everything that we just said, so you can read that for yourselves. And now we can go from accumulation. We went before from depletion to flat band to accumulation. Now we're adding the right side of the chart. We can go from accumulation, we apply a more positive voltage to get to flat band, and then we go to depletion by making it more positive. Yet, generally, for reasonably well-designed structures, this would be a zero external bias. But we could have a situation, we'll see that in a little bit, where for zero external bias, we're in accumulation. And there we apply a positive bias, and we can keep going to depletion. Eventually, the Fermi level crosses the intrinsic, and then we get into what we call weak inversion, and we continue more positive for the external bias, and we get to something called threshold, which we'll talk about quite a bit, and then we get into strong inversion. And this is the region right here where we really can make use of this structure to make a practical device. Okay. So now we go through the same thing that we did before pictorially, but now we're going to add this thing called phi B. Phi B is the bulk potential, and it's simply the distance between, I should say not the distance, the level of the intrinsic. Let me move that bad boy over here. Above the Fermi level. So in this case, the Fermi level is below intrinsic, so we have a p-type substrate, and we're going to kind of use a default as being 0.42 EV, which is 10 to the 17th doping in the p-type substrate. So this distance right here, the arrow would be 0.42 EV. In this case, we have accumulation because we have a negative charge at the metal oxide interface and positive at the oxide silicon interface, and the band bending is very, very low. Little bit bending up. In depletion, we have the opposite effect, but here there are just fixed ions. That's why the intrinsic has not yet crossed the Fermi level, and of course the phi B is still 0.42 electron volts. In weak inversion, it's just crossed the, it is the intrinsic level, has just crossed the Fermi level, so we get a little bit of surface electrons. I should point out that this is not a terribly useful device. In fact, it's, well, to euphemistically say, it's bad news. It's why your laptops get hot. We don't want any electrons here in weak inversion. It's not strong enough. There's not enough of them to make a real channel, but there's enough of them to cause havoc, especially when there's a couple billion in your laptop. So this is not a desirable situation, but it's there, and there's nothing we can do about it. Okay, so here we are at threshold. And at threshold, we have just a number of negative charges to completely, or well, close to completely, shielding the interior part here. This is still the depletion region, but it is further into the silicon and does not allow the electric field, which emanates from the positive charge at the metal oxide interface, to penetrate deeply and uncover more negative ions. Up here in the weak inversion, every other electron is able, well, I should say every other hole that is applied to the metal oxide interface by applying a more positive bias does two things. It attracts an electron to the oxide silicon interface, but it also can uncover some negative fixed ions. So we get a little bit of band bending in weak inversion as those fixed ions are uncovered, and we also get more electrons at the interface. And at threshold, we have just enough electrons at the interface to shield the electrons, or the, I should say, the fixed ions in the depletion region. And just one more comment. When that happens, if we increase further the voltage, the applied voltage VG, making the metal oxide interface even more positive, essentially no more fixed ions are uncovered, and therefore no more band bending. And that happens approximately when the amount of band bending from this point to this point is equal to twice the bulk potential. So the bulk potential from intrinsic to the surface is phi b, and of course the bulk potential from intrinsic, from the formula, I should say, let me go back and say that again. The band bending from the Fermi level to the surface is phi b, and of course the bulk potential in the interior from the Fermi level up to the intrinsic is also phi b. So the total band bending is twice phi b. So that's the proposition, and we can check that for two extreme cases. One for heavily doping, which should be 10 to the 18th. That's really heavy, about 10 times heavier than our default of 10 to the 17th, and for very light doping of 10 to the 15th. So for heavy doping of 10 to the 18th, the depletion region is scrunched up. A lot of negative ions, but they're very close to the surface. So therefore, I need a lot of electrons at the interface in order to shield those negative fixed ions. If the substrate is lightly doped, 10 to the 15th, then of course W, the distance here, is much greater. The charge density is much less. These fixed ions extend back much further into the bulk, and I don't need nearly as many electrons at the interface to shield them. So if I have 10 to the 18th doping, I need about 10 to the 18th fixed electrons to shield them. If I have 10 to the 15th doping in the bulk, I need much less, approximately 10 to the 15th. So above that level, above threshold, if the gate voltage is made higher than threshold, the amount of increased band bending is essentially nil, and all of the charge which goes to balance the positive charge consists of surface electrons, and I have a nice healthy channel, and I can make a quite useful device, to say the least. Okay, so I think this sentence basically sums up the whole argument here. At threshold, the depletion width essentially ceases to increase even as the gate voltage increases. All of the electrons go into surface electrons to make a channel. Okay. Now, if we apply an external gate bias, we know that the bias from the metal to the silicon, this bias right here, is distributed between the oxide and the drop across, drop across the oxide plus the drop across the silicon in the depletion region. And we see that because the band bending is in the same direction. So we're tempted to write that the gate bias is simply equal to the voltage across the oxide plus the voltage drop across the silicon. And that is not quite right. And the reason that it's not quite right, it makes sense, but we know, in fact, in our previous work, we've known that even if Vg is equal to 0, we can still have drops across the oxide and across the silicon. It's very possible with no applied bias that I have a depletion region. And if I have a depletion region, then I have a V sub phi sub s band bending, and I know that V sub ox must be equal and opposite to that as far as the voltage drop goes. So we need to modify this relationship, and the way to do it is we stick in the flat band voltage. So this is really the full correct equation. Vg minus VFB is equal to Vox plus phi s. And in this equation, there are three variables: gate voltage, the oxide, the S. They're all related by a linear equation, and one constant. And the flat band voltage does not depend on the gate voltage. It is a constant of the material. It only depends on the work function difference. Okay, so this equation kind of makes sense because we've got to have something that depends on the work function difference. And we stick in a minus VFB, minus the flat band voltage. Let's check it out. Let's see if it works. And we're going to do that for two extreme cases. One case where the metal work function to silicon work function is about magnitude of 1 eV, or 1 volt, and the other where it's essentially 0. So the first case is we have N++ silicon or aluminum. They both have work functions about 4 electron volts. N++ silicon, the Fermi level is right up at the conduction band, and that's the same for aluminum. And if we have 10 to the 17th for the doping, which is very close to the valence band, the Fermi level would be close to the valence band, we have about a work function difference in magnitude of about 1 eV. I should perhaps have written 1 eV or 1 volt. And the reason that the silicon work function is about 5 is because it has the affinity of silicon, which is about 4, plus 1/2 the band gap, which is about 0.56, plus about 0.42. I think we've gone over that before, so it works out that this is about 4.98 or close enough to 5. So this equation we've seen before, and that makes sense. So the bottom line is that with no gate voltage, the structure is in depletion. And we know that because the work function in the metal doesn't look like metal, but that really is metal. Could be aluminum, could be generally doped silicon, is much smaller, in fact 1 eV smaller than the work function in the silicon. So let's now flatten out those bands. So here's the bands in depletion, and we want to flatten them out. So we have, with no gate voltage, we have positive on the metal oxide interface, negative fixed ions in the depletion region. The field points from left to right in the positive direction, so we need to counter that by applying an external voltage, which is negative on the metal oxide interface with respect to the silicon. So it's positive in the silicon, negative in the metal. It goes from right to left, which is the negative direction. And how much do we have to apply? Well, we have to apply the work function difference. So minus, because it's negative direction, 1 volt. So then, equation 17.3 becomes Vg minus VFB, which is minus 1 volt, which is Vg plus 1 volt equals Vox plus V sub S. And of course, if Vg is equal to VFB, namely minus 1 volt, this left side becomes 0, and we have Vox plus V sub S, the drop across the oxide, plus the drop across the silicon is 0, and because these are passive elements, the only way that that could happen is both Vox and V sub S must be precisely 0. Okay, so now let's look at the other case, the other extreme case, where instead of having n++ with a small work function, we have p++ with a big work function. That's certainly possible, not desirable, probably is a mistake, and I've worked long enough in fabs to know that mistakes, guess what? They happen all the time. So anyway, we now have a higher work function in the metal than in the silicon. The work function in the metal is approximately 5.2. By the way, this could be nickel. Rather, it could be gold, but I suspect we would not want to use gold in a silicon fab. So it could be nickel, gold, or P++ silicon. The work function is about 5.2. The work function of the silicon is, as it is before, about 5. Where is that? Somewhere up here. So the difference, again, we'll call it the magnitude, is about 0.2 volts. In this particular case, we have accumulation. So the bands bend up just a little bit. I've probably shown it a little bit too much here. There's a very slight band bending. The surface is actually more positive than the bulk. And we have a very slight negative charge on the metal oxide interface. And notice the bands bend in the same direction, but in the opposite direction to the previous case. So hopefully all that makes sense. Now here we want to put we want to flatten out those bands. So we want to put a positive bias on the gate with respect to the silicon. So therefore the external field is from left to right, in the positive direction, so the V flat band is, which is a external bias, it is positive because the field is in the positive direction. So we write equation 17.3 immediately. And again, if Vg equals to the flat band voltage, 0.2, this term, the left side goes to 0, which means that there is no voltage across the oxide and there's no voltage across silicon, and the bands are flat. If Vg is more negative than +2, we go into a deeper accumulation. And for Vg more positive than +2 volts, we go into depletion. Okay, so now let's look at these things a little bit more quantitatively. This is going to be our first quantitative shot at this. We're going to do a little bit of work, and we're going to get a little bit of information. So that's okay. The trade-off. We don't do too much work, but unfortunately, we're going to have to do it again in much more detail later on, and we'll get much more information. So we start with the fact that in accumulation, the band bending is approximately 0, and in inversion, the band bending has reached its maximum value. By that I mean if we increase the gate voltage in a positive way, we don't increase the amount of band bending. So as the structure moves into depletion from accumulation, the voltage across the oxide as well as the band bending, they both increase. Both the Vox and the V sub S increase in depletion as we go more and more positive on the gate voltage. So we can say in the depletion mode, when we have this band bending, which we've seen up here, we can write a relationship that the voltage across the oxide is equal to the charge on the oxide, either on the left or the right side, they're both equal, divided by the oxide capacitance. And all of this is aerial. We have sort of siphoned off the cross-sectional area. So we have to keep that in mind when we look at the units. So the charge on the right side in depletion, this charge is equal to the, well, it's equal to the charge density here, charge density multiplied by the depletion width. So charge per cubic centimeter multiplied by the width if we siphon off the surface area. So this would be just in coulombs. It's really coulombs per square centimeter, but we're not worried about the square centimeters. Anyway, the charge density is just Q, the electronic charge, multiplied by the doping. In this case, we probably could have and should have written Na rather than just N, because in P silicon, which is our default structure, then the doping is acceptor doping. Okay, so really now what we have to find is W, but we know W. Here it is. It's the same as a Schottky, and you've seen that in the Schottky, we've seen it in the PN junction, all the same. So the depletion region width is just proportional to the band bending divided by Q times the doping, all to the 1/2. So basically all we do is we take equation 716 and we dump it into equation 17.5, and therefore the Qn flips from the denominator to the numerator, and there it sits. This is the voltage across the oxide in depletion, and that's a really important relationship. So now we can write equation 17.3, Vg minus VFB is the drop across the oxide plus the drop across the silicon. Okay, so let's keep going and looking, see if we can take this thing apart in a little bit more detail. And it's going to be a little bit tricky, a little bit of work, because I've got phi sub s in two places, one on the square root and one without a square. So let's look at band bending in an NMOS structure at the oxide silicon surface. And if I didn't explain what NMOS is, NMOS just means that we have a P substrate and we invert it to N-type at the oxide silicon surface or oxide silicon junction so that we have a channel. So this is NMOS, which refers to P silicon and an N channel, whereas PMOS refers to N silicon and a hole channel, a channel of holes. Okay. We're generally going to be using NMOS. Okay, so we have a P-type structure. In this particular case, we have an external voltage, and we are probably in weak inversion because the intrinsic layer is below the Fermi level, but this is the bulk right here. This would be about 0.42, and it looks to me like this distance here is significantly less than 0.42. So this would be in weak inversion, and here we see the total amount of band bending and the depletion width. Okay, so let's just go through this exactly that we did before. A little bit different notation, but the same idea. Start with equation 17.3, which we have rewritten as equation 17.9. Same equation, Vg minus Fb, and it's dropped across the oxide and across the depletion region in the silicon. And then the band bending, which is, in this case, in electron volts, Q times phi sub s is equal to E sub I in the bulk minus E sub I in the surface. We just take the difference between this value here and this value, and we get the total band bending. So that's a trivial equation, but let's write it down. And again, we write down an expression for the depletion width. The higher the doping, the smaller the depletion width. All the charge is scrunched up into a small value of W, and of course, the higher the amount of band bending, the greater the W. And epsilon here refers to the permittivity of the silicon, which I believe is 1 times 10 minus 12. Okay, so for some reason I just wrote that again, and this is our expression, remember, for the Schottky barrier, but it's the same thing. P-N junction, Schottky barrier, NMOS, all the same, and that's a good thing. And I probably shouldn't have written an A here because, well, for Schottky barriers, we generally use a donor dope. So this would be ND. For our case here, we have N sub A acceptor doping. Okay. Now, before we were looking at, we wrote an expression for Vox, but Vox and Vdep, I'm sorry, not Q. Qox and Qdep are the same thing. Qox is the charge here, which must be exactly balanced in depletion by the charge in the depletion region, Qdep. So the charge here and the charge here are precisely the same. When we get into inversion, there'll be another charge, and that'll be called Q inversion, oddly enough. Okay, so we just wrote that here as Q depletion. Same exact formulation. It's equal to uh, the charge. What are the units here? The units here are coulombs per cubic centimeter. So it's the charge density multiplied by the depletion width. So the total units here, or I should say total units, the units here are coulombs per square centimeter. But recall that we have siphoned off the square centimeter because the square centimeter is basically the depth into the device multiplied by the height, and everything is normalized, so we don't consider that. So this is not the total capacitance, it's rather the areal capacitance in farads per square centimeter, not in farads. So Q dep, the units are coulombs per square centimeter. So we just substitute again for W, just like we did before. We get exactly the same relationship, and this is the same relationship we had previously for the voltage across the oxide, and we had the same equation. And now we're going to solve the equation. Okay, so the equation is quadratic in the square root of, this should be not psi sub s, that should be phi sub s. So correct that. That is nasty of me to make that mistake. Anyway, it's quadratic in phi sub s. So here we have it. It's basically just a quadratic equation. And A and B, see B is the term without the square root. That's just VG minus VFB. And A is all of this stuff without the square root of phi sub s. So that's what we have here. And we can just solve now for the square root of phi sub s. And there it is, just using the quadratic formula. So we won't go through that. That's high school algebra. And then we substitute in for A and B. Fairly straightforward, at least conceptually. Unfortunately, a little bit of algebra, but nothing is conceptually difficult here. And then finally, we want to get the total band bending, so we just square this guy. Square on the left side, and we square on the right side, and that's what this 2 is right here. And this is it. That's the equation that we seek. Not conceptually particularly sophisticated, but unfortunately a fair amount of algebra. We don't get a great deal of information, but we get some. And let's consider first with no applied bias. So if we have no applied bias, then we have that VFB is equal to VBI. That's the band bending with no applied bias. So the first case we consider is when Cox approaches infinity. That's a really good case. That's what we'd like to see. Unfortunately, we can never get there. That's if there's no barrier width at all. So we have really good control. The gate has really good control over the silicon. In that case, all of this stuff is really, really big. In fact, we're going to allow it essentially to go to infinity. Certainly much greater than 1. So we just take the 1's away, and we have immediately that the band bending is equal to this term times this term. And this is what we get. And when the dust settles, everything cancels out, and we get VBI, exactly what we had for a Schottky barrier. So that's, or I should say, a rectifying Schottky barrier, or rectifying metal semiconductor structure. That's when you have the oxide basically going to 0. And instead of being this distance or this dimension, it essentially goes away. So Cox essentially goes to infinity. And that's right here. Okay. I take it back. We haven't gotten there. That's here. Okay, so the band bending is equal to the barrier just like we had in the Schottky barrier. So now we take a case where Cox is small. That is not good. I can emphasize the not here. Cox is small means that this dimension, oh, it must be someplace, is really, really big. So we have very little control of the metal on the silicon. All the voltage is dropped, or almost all is dropped across the oxide. And that is not a good situation. And that is case number 2. Take a look at that. Where is that? Someplace here. Okay. Yeah. Okay. So Cox is very small. Then we just call this A. A is much smaller than 1. So we can expand 1 plus A is approximately equal to 1 plus A divided by 2. And we put all that stuff in here. And we get that the band bending is equal to this guy right here. And you see that is certainly not VBI. It is VBI multiplied by very small numbers. Cox is very small, and the number here doesn't do too much to make it any better. So this is much smaller than VBI, and it just says that all the voltage, or the vast majority of the voltage, is dropped across the oxide, and that is not a desirable situation. So we just do an example here, and for Tox, this would be 1,000 angstroms, 0.1 micron. That's really, really big. That was not big 20 years ago, but today it's really big. Of course, our standard doping is 1 × 10⁻⁷, and we get a Cox, which is very small indeed. We would like to see this not 10⁻⁸, but 10⁻⁷, or even 10⁻⁶. And again, this is per square centimeter. And then we get, just to check, this is a sanity check, we assume that A is small, and indeed that is the case, that A is much smaller than 1, so we can use this approximation. Okay, case 3, Cox is large, but it's finite. It's not infinite. It's not that big. So then we get a, for example, what do we do? 25 angstroms. 25 angstroms is doable. It is fairly thin, but I think there are cases say where it's even thinner. And we get an aerial capacitance not of 10⁻⁸, but of 10⁻⁶. And that's a good number. That's a really good number. That's farads per square meter, per square centimeter. And then A is about 24. So in that case, A is quite large. And we can do a different approximation here. So if A is much bigger than 1, then we get this approximation here. We keep substituting, and we find the surface bending is equal to, or given by equation 17.25, and if we had covered this up, we had the band bending equal to VBI, which is the Schottky, when we have infinite Cox. If we have large Cox, but not that large, reasonable Cox, then the band bending is reduced by this value here, and all that makes sense and is completely consistent. Okay, this is probably a good place to stop, because next time we want to talk about threshold. Threshold is a really, really big deal. So I don't want to start on something that's rather challenging. We'll take that up next time. Let's skip all the way down. Oh boy, there's a lot to skip over here. Go down to our final video clip. This is one of the many powerful scenes from the movie Grapes of Wrath. If you haven't read the book by John Steinbeck, go out and read it. It's a fabulous book. It's a fabulous movie. I believe it was 1939 or 1940. Linda Darnell as Ma, and the incomparable Henry Fonda as Tom Joad. and we'll see you next time.
Well, maybe it's like Casey says. The fella ain't got a soul of his own, just a little piece of a big soul. The one big soul that belongs to everybody.
Then what, Doc?
Then it don't matter. I'll be all around in the dark. I'll be everywhere, wherever you can look. Wherever there's a fight so hungry people can eat, I'll be there. Wherever there's a cop beating up a guy, I'll be there. I'll be in the way guys yell when they're mad. I'll be in the way kids laugh when they're hungry and they know supper's ready. And when the people are eating the stuff they raise and living in the houses they build, I'll be there too.
I don't understand it, Doc.
Me neither, Ma, but just something I've been thinking about. Give me your hand, Ma.